Go.
Hello, my dear students, and welcome to our video help session for um, our first exercise in chapter 3, where I've given you a set of equations, 10 reactions, chemical reactions, where you need to balance the equations so that they follow the law of conservation of mass. Now, in our case, we're going to conserve mass because that mass, that matter, those elements are conserved from one side of the reaction to the other. Remember, the way the atoms are arranged changes, but the number and type of atoms from one side to the other of the equation cannot change. Now, some of you have discovered that these videos appear on my YouTube channel before I get them posted to our Blackboard course shell. That's fine. You're welcome to go into YouTube. If I post them to YouTube, I've started posting some others, and so far it's taken 4.5 hours, and they're only 30% done, less than 30% done. So as soon as they get onto YouTube or the very next day, I always sweep them into the Blackboard shell. But you can find some of these in YouTube sooner at my YouTube channel. Subscribe, like, or don't like. But the YouTube channel for all of my videos, and you'll see a lot of videos from older courses, other courses, and even some biology as well as chemistry in there. You'll see other things that may not be germane, but you can pretty well assume the new ones are for you. Those are found in the YouTube channel called Dr. Mark Shanley, DrMarkShanley. Search for that when you get in YouTube and you'll see him, if you want to get him maybe a day early at most. We had 10 practice equations, and I've recreated them here, written them on my kitchen wall here, and I want to just quickly balance them and show you the technique. It's kind of like working a crossword puzzle. You fill in what you know, you get what you can, and that will lead you and give you clues to the rest. And you just try and make things match. It's often simply trial and error. Okay? When you're given everything like this. Now, if I were giving you, for example, the names iron and iron, what is this? Iron 3 sulfate, then you might have to deduce some structures and the like. But for this is very straightforward. I just need the number of iron atoms on each side to be the same. So I look at this reaction of iron plus sulfuric acid forms iron sulfate plus hydrogen gas. Okay? This is elemental iron. This is sulfuric acid, H2SO4. This is iron 3 sulfate, and this is hydrogen gas. And I need to balance it. Well, and I need to be careful because I can't erase. But if I have, for example, 2 irons here, I know I'm going to need at least 2 over here. And if I have 3 sulfates over here, I know I'm going to need at least 3 of these. And now, so far, I have 3 sulfates on this side, 3 sulfates on this side. Good. 2 irons on this side, 2 irons on this side. If there's one of these, and that would leave me with 6 hydrogen atoms. Hydrogen is a diatomic gas, so I would have 3 of those for a total of 6 hydrogen atoms. And by the way, that is balanced. I don't have to try anything else. So let's go to the next one. This is silicone tetrachloride. It's actually a liquid. Its other name is trichlorosilane. That's the way I learned it. That's a trivial name. It's silicone tetrachloride, according to its formal name, plus water. We do not say dihydrogen monoxide. The trivial name water will do because it's in universal use. This is silicone dioxide plus HCl, or hydrochloric acid. This one has some symbols along underneath it, giving the states. Liquid silicone tetrachloride plus liquid water gives solid silicone dioxide plus hydrochloric acid dissolved in water or aqueous. If we were to put them into the previous one, hydrogen is a gas. The iron sulfate is a soluble salt that is aqueous, AQ, dissolved in water. Sulfuric acid, dissolved in water, and iron is solid. This is someone dropping a bar or some iron into sulfuric acid. Here, I'm mixing two liquids and a solid comes out. By the way, this silicone dioxide is silica, also known as silica. What you find in quartz, what you find in most of the sand in the world, very common compound. You heat it up and cool it down, it becomes glass. So anyway, I have 4 chlorines over here in this compound and 1 over here. So, what am I going to do? If I have 1 of these, I have 4 of these. This has 1 silicone, this has 1 silicone, but I need 2 oxygen. But I had 4 of these, so I need 4 hydrogens, so that would work if I do 1 of these, 2 of these, right? That would give me 1 of these, 1 silicone here, 1 silicone here, 2 hydrogen here, and 2 times 1 oxygen. 2 oxygen here, 2 times a single oxygen here. So that balances. I have 4 hydrogen atoms, unaccounted for, and 4 chlorines, but that would give me 4 of those. That's balance. I'm going to do every other one this time. You're going to do the others. Okay? So, I warned you, I'm not going to answer every one. I want to get through this quickly. This next one is kind of interesting. This is one I had to work twice. Ammonia. This is ammonia. It's a gas. Combined with oxygen gas gives this compound NO. I learned it as nitric oxide. People still call it that. It's really nitrogen monoxide. You don't have to say mononitrogen monoxide, but it's nitrogen monoxide. Has some interesting properties, and of course H2O is water, and probably in this reaction it was at high temperature. That could be gas. If it's room temperature, it would be a liquid. Okay, I could go either way with that, but when I do this I see, let's see, I got 2 here, and I've got an even number of hydrogen here, but an odd number here. So I'm going to have to multiply this one by some even number, 2, 4, 6, or 8. When I tried 2, I had 2 ammonias, then I have 2 nitrogens here, and 3 waters here. But now I have 2 and 3, that's a 5. And I need an even number over here. And if I were doing this on a board where I could erase, I would have tried that and shown you. But since that doesn't work, what I do with this one is, instead of the 2, I try a 4 here. I'm just thinking ahead. I know that that worked for me. So I have 4 of these and 12 hydrogens. 3 times 4 hydrogens, okay? So that gives me a 6 here. If it doesn't work, I just erase it and try it again. But this gives me 6 oxygens here And I know I have 4 nitrogens here. So this is 4 oxygens here and 6 oxygens here. That's a total of 10. So I would need 5 diatomic oxygens to get 10 oxygen atoms. And so this one is 4, 5, 4, 6 are the what? Coefficients for these. Remember, you can only change the coefficients. You may not change the subscripts. If you change the subscripts, it's a different compound. So you can only change the coefficients. What about for testing purposes? What I'll do is, for example, I'll label these A, B, might not be a good example, C, and D. You know, I might label them W, X, Y, and Z. And then I'll say, what's the coefficient for A? And your choices would be, 1, 2, 3, 4. Ding, 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 and you would choose 4. Like A1, B2, C3, D4. And you would choose D on a multiple choice objective exam. So that's how I test for this in an exam. I can take one equation and ask a bunch of questions off it. This next reaction is very interesting. It's silicon dioxide. That's that silica. It could be glass. Plus HF, hydrofluoric acid. This is the one acid that dissolves glass. I cannot keep hydrofluoric acid in a glass container. It'll leak through it. Artists and people use this. You can buy it at MJ Designs or Michaels and get HF, at least in a paste, that you can put on glass to etch and frost glass because it dissolves the glass. You paint it on and you come back hours or later or the next day and wash it off and it's been dissolved. And so this is hydrofluoric acid. We keep it in a plastic bottle. And then it gives silicone fluoride and silicone tetrafluoride and water. So when I do this, I have 1 silicone here, 1 silicone here, 4 fluorines. So let me try a 4 here. And that would give me 4 H's. So that would mean I could make 2 waters. I need 2 oxygens. I have 2 oxygens. And there's 1, 4, 1, 2. Those are your coefficients. Last one was a really hard one. It's one I would never give you on a test because I've said many times I'll never give you any equations to balance where I jokingly say you have to take your shoes and socks off. I'll never go over 10. And really, as you can see, the majority of them are really under 5. There's a 6, there's a 5, and we're going to see a couple big numbers down here. This is a reaction of ammonium phosphate, fertilizer, although not always in that form, plus lead nitrate, a toxic compound, probably used as a pigment in paints. We don't deal with much lead anymore. Lead nitrate here. Lead nitrate is soluble, but still toxic because you have this lead. And it's lead 4 nitrate because there's 4 nitrates. Nitrate is always -1. According to, in your book, your chart of common ions, and your polyatomic ions, nitrate is always -1. Phosphate is always -3. This is the ammonium ion. It's always +1. So you can see this -3 took 3 of these. But this is already, these compounds weren't named. They were given to you. So we know how many atoms of everything I need. And here is ammonium nitrate, a great fertilizer because 2 different sources of nitrogen in it. And I'm sorry I didn't write this out right, but this compound has 3 leads. And so I know I'm going to need at least 3 over here. So let me start with a 3 there. Well, this lead nitrate, every molecule of this lead nitrate has 4 nitrates for every lead, because this lead has a +4 charge. Nitrate's -1. So that means I would make 12 of these nitrates. 12 of these. So let me try a 12 there. Woo. That's a bigger number than I like dealing with in a coefficient, but it's still manageable. And if I do this and make one of these, sorry to put it up there, I forgot to leave a space, then I would have 4 phosphates, right? And there's only one in this, so I would do 4 of those. And if I did that, I would have 12 ammoniums, because there's 3 ammoniums in each ammonium phosphate, and if I have 4 of them, 4 times 3 is 12. So I have my 12 ammonias, 12 of those and 12 of those. I have my nitrates. I have 12 here, and 3 times 4, before it was 4 times 3, 12 here. I've got 3 leads here, 3 leads here, and 4 phosphates here, and 4 phosphates here. So this one was really kind of hard. If you're thinking ahead and you've done it, it's kind of quick. I do want to go back to some of these compounds and talk about them. This nitrous oxide is a common pollutant that forms between nitrogen and oxygen in the engines of your car at high temperature. The atmosphere is 20%, 19% oxygen, 70% nitrogen. You get some high temperatures in that car engine and you produce this. It's a common environmental pollutant. This is why you have catalytic converters, so that you can convert this to nitrogen and oxygen. This has profound effects in the body. It has the effect of relaxing blood pressure, blood vessels, to control blood pressure. For example, people having a heart attack may take a substance, nitroglycerin, that releases this substance that relaxes the vessels of the heart, so that the heart can receive the blood it needs to continue to pump. People who have erectile dysfunction take Viagra, which specifically targets blood vessels in the corpus cavernosum, so that the nitrous oxide relaxes those blood vessels and you get better blood flow. But profound effects on the body. It controls some aspects of the immune system. It's an important neurotransmitter. And so it's also a common environmental pollutant, and is actually, if you breathe it as a gas, not producing it in small amounts in your tissues by an enzyme. I want to say it's called arginine oxidase. There's an enzyme in your tissues that breaks down the amino acid arginine, and a side product of the reaction, or a product of the reaction, is NO. And that reaction is highly regulated, of course. But when it's not regulated and you have school children breathing this in, it causes all kinds of problems. So it's also a leading cause of acid rain. So why are we learning chemistry? I'm just giving you this extra stuff, which I'm not going to test over, because it's important to know how and why things work. This dissolves in water to make H, a couple of waters, HNO3 plus H, which is nitric acid, which is destructive to, so many things dissolve in it. Marble statues, steel buildings, your car's paint finish. You don't want acid rain if you can avoid it. And for the most part, we control it now that we have catalytic converters on our cars, and we control the pollution output of our factories. So we don't have the problem with acid rain that we had back when I was in college and learning this in the 60s and 70s. So just wanted to make some comments about those. Practice doing the other 5, hand it in. Here's half, so nobody needs to make less than a 50 on this assignment. And until the next one, you're going to have two or three more assignments. I've broken it up into three. I don't know how many help sessions I'll do for the rest of chapter 3. So until the next one, goodbye.